Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Google, Prompt Engineering, February 2025. When you type into a chatbot, you're already doing prompt engineering. A prompt is simply the input an LLM uses to predict its next tokens. But getting from a casual question to a precise, reliable result is not automatic. The model you choose, its configuration, and how you phrase and structure your prompt all matter. In this talk, we'll walk through practical techniques for prompting Gemini models in Vertex AI or via API, and show how to move from ad hoc chatting to deliberate, repeatable prompt design. Under the hood, a large language model is a prediction engine. It reads your prompt as a sequence of tokens and repeatedly predicts what token should come next based on its training data. That means your prompt is really a way of steering the model's prediction path. Change the wording, structure, or context, and you change that path. Because of this, prompt engineering is inherently iterative. You try something, see how the model behaves, and refine until the output matches your needs. Before you even write a prompt, you need to pick a model and set its configuration. Whether you're using Gemini, GPT, Claude, or an open source model like Gemma or Llama, the same idea applies. The model plus its settings define how it behaves. Output length controls how long the answer can be. Sampling controls like temperature, top K, and top P control how deterministic or creative the model is. And remember, more tokens mean more compute, higher latency, and higher cost. So configuration is part of prompt engineering, not an afterthought. The max output length setting is often misunderstood. It doesn't make the model more concise. It simply stops generation once the limit is reached. If you want short answers, you must both set a reasonable token limit and explicitly ask for brevity in the prompt. This is especially important for techniques like ReACT, where the model may keep emitting tool calls or commentary long after you've gotten the answer you care about. It's also crucial when generating verbose formats like JSON or code, which can quickly run into token limits and get truncated. LLMs don't pick a single next token. They assign probabilities to many possible tokens, then sample from that distribution. Temperature scales how sharply the model prefers high probability tokens. At temperature 0, it always picks the most likely token, giving you deterministic, stable outputs. As you raise the temperature, lower probability tokens become more likely, which is great for brainstorming or creative writing. Top K and top P further restrict the candidate tokens. Top K keeps only the K most likely tokens, while top P keeps the smallest set of tokens whose cumulative probability exceeds P. The right combination depends on whether you want reliability or variety. The simplest way to prompt is zero-shot. You describe the task and let the model infer everything. That can work surprisingly well, but it's not always reliable. One-shot prompting adds a single example of input and desired output, which already helps the model lock onto the pattern. Few-shot prompting goes further by giving several examples. This is like showing the model a mini training set inside the prompt. For many tasks, classification, extraction, formatting, few-shot prompting can dramatically improve accuracy and consistency. Modern LLM APIs often separate different parts of the prompt. The system prompt sets the overall behavior, things like safety, style, and what the model is allowed to do. Role prompts tell the model who it should act as, for example, a security analyst or a travel guide. Context prompts supply the specific information it should use, such as documentation, emails, or database results. By carefully designing these layers, you can control not just what the model answers, but how it reasons and what information it relies on. Step-back prompting is a simple but powerful trick. Instead of answering directly, you first ask the model to step back and describe the problem at a higher level. For example, you might say, "First, explain what this question is really asking, then answer it." This encourages the model to form an abstract representation of the task before diving into details. Research shows that this kind of abstraction can improve reasoning quality and reduce brittle, surface pattern answers. Chain of thought prompting explicitly asks the model to show its reasoning. Instead of jumping straight to an answer, you instruct it to think step by step or to explain its reasoning before giving the final result. This often unlocks much stronger performance on tasks that require multiple logical steps, like math word problems or nuanced classifications. In practice, you'll want to structure your prompt so that the final answer is clearly separated from the reasoning, making it easy to parse programmatically. Even with chain of thought, a single reasoning path can go wrong, Self-consistency tackles this by sampling many reasoning paths and then letting them vote. You run the same prompt multiple times with a non-zero temperature, collect all the final answers, and pick the one that appears most often. In the email classification example from the paper, different reasoning chains alternately labeled the email as important or not important. When you aggregate many runs, the correct label, important, wins out. This ensemble of thoughts often yields more reliable answers than any single run. Chain of thought follows a single linear reasoning path from start to finish. Tree of thoughts generalizes this idea by exploring multiple branches of reasoning in parallel, backtracking when a path looks unpromising. Visually, you can think of COT as a straight line of thoughts, while TOT is a branching tree where each node is a partial solution. This figure captures that contrast and sets up why Tree of Thoughts can handle more complex exploratory tasks.
Tree of Thoughts takes the idea of chain of thought and turns it into a search problem. Instead of committing to one linear chain, the model generates multiple partial thoughts, evaluates them, and decides which branches to extend. Each node in the tree is a coherent chunk of reasoning. By exploring, pruning, and backtracking, TOT can tackle tasks that require exploration, like puzzles, planning, or combinatorial search, much more effectively than a single straight-line reasoning path. REACT stands for reason and act. Instead of just thinking in text, the model alternates between reasoning steps and concrete actions, like calling a search API or running code. The loop looks like this. The model thinks about what it needs, calls a tool, observes the result, then thinks again. In the Metallica example, the agent repeatedly searches for each band member's number of children, updates its internal count, and eventually returns the total. This pattern is the basis for many LLM agents that can browse, query databases, or orchestrate workflows. Writing good prompts by hand can be tedious. Automatic prompt engineering turns the model into a prompt generator. You start with a meta prompt that asks the LLM to propose many candidate instructions for your task. For example, different ways customers might order a Metallica t-shirt. Then you evaluate those candidates using a metric like blue or rouge or task-specific accuracy and keep the best ones. You can tweak and rescore them, gradually converging on high-quality prompts with far less manual experimentation. Gemini and similar models are powerful coding assistants.
You can describe a task in plain language, like renaming all files in a folder, and have the model generate a Bash or Python script. You can paste in existing code and ask for an explanation, which is great when you inherit someone else's project. You can also translate code between languages or ask the model to debug errors and suggest improvements. The paper walks through a full example, generating a Bash renamer, explaining it, translating it to Python, then debugging a broken version with the model's help. For debugging, you can treat the LLM like a very fast code reviewer. Provide the traceback, the offending code, and a clear instruction such as, debug what's wrong and explain how to improve this code. In the example, the model not only fixed the undefined toUpperCase call, but also pointed out other issues and proposed a more robust implementation. That said, LLMs can't run your code or fully understand your environment, so you must still read, test, and validate everything they suggest.
Prompting isn't limited to text. Multimodal models like Gemini can accept images, code, and other formats alongside text. You might show a screenshot and ask for UI feedback, or provide a chart and ask for interpretation. The same principles still apply. Be clear about the task, provide examples when possible, and specify the desired output format. Multimodal prompting simply widens the range of inputs you can use to guide the model. One of the strongest levers you have is examples. Instead of just telling the model what to do, show it. For classification, extraction, or formatting tasks, a handful of well-chosen examples can dramatically improve accuracy. Make sure your examples use the exact style, tone, and structure you want in the final output. Think of them as tiny, embedded training sets that teach the model how to behave on similar inputs. Complex rambling prompts usually hurt more than they help. If your prompt is hard for you to parse, it's likely hard for the model as well. Aim for short, direct sentences and verbs that clearly state the action. Act, summarize, classify, extract, rewrite, and so on. The paper shows how a long, chatty question about visiting New York can be rewritten into a crisp instruction. Act as a travel guide.
described great places to visit in Manhattan with a 3-year-old. That kind of clarity pays off.
Models are not mind readers. If you want a 3-paragraph blog post in a conversational tone, say exactly that. If you only care about certain fields, like console name, company, year, and total sales, spell those out. Research suggests that positive instructions, telling the model what to do, are more effective than long lists of what not to do. Use constraints sparingly, mainly for safety or when you truly need to forbid certain content. Clear, specific output instructions are one of the easiest ways to boost quality. When you move from experimentation to production, you don't want dozens of nearly identical prompts hard-coded everywhere. Instead, design prompts with variables. For example, you are a travel guide. Tell me a fact about the city. Your application can then substitute Amsterdam, Tokyo, or any other city at runtime. This makes prompts easier to maintain, reduces duplication, and keeps your logic consistent across different use cases. The way you phrase a task matters. Asking a question, making a statement, or giving an instruction can all lead to different outputs, even if the underlying task is the same. For classification with few-shot examples, don't always present classes in the same order. Mix them up so the model learns the actual features of each class, not just the sequence. A good starting point is around 6 examples. From there, you can add or remove examples and watch how accuracy changes. For tasks like extraction, ranking, or classification, free-form text is often a headache. Instead, ask the model to return JSON or another structured format. This forces it to organize information into fields, which tends to reduce hallucinations and makes integration into downstream systems much easier. You can sort, filter, and validate the data programmatically. The trade-off is that JSON is verbose, so it uses more tokens and is more likely to be cut off if you hit output limits. Tools like JSON Repair can help fix truncated or malformed JSON when that happens. You can go a step further by using JSON schemas. A schema describes the structure and types of your data, fields like name, category, price, features, and release date for a product. Instead of dumping raw text into the prompt, you provide the schema plus a JSON object that conforms to it. This gives the model a clear blueprint of what each field means and how they relate, which helps it generate more accurate, focused descriptions or analyses. Schemas are especially useful when you're working with large, structured datasets or building complex applications. Prompt engineering benefits from collaboration. Different people will come up with different angles and phrasings, and some will perform much better than others. To manage this, document your attempts. The paper suggests a simple template. Record the prompt name and version, goal, model, temperature, token limits, top K, top P, the full prompt text, and representative outputs. Store this in a shared sheet or system. When the model is updated or you change configurations, you can quickly rerun and compare instead of starting from scratch. For chain of thought, structure matters. Always have the model present its reasoning first, and then clearly mark the final answer, for example, with a line like final answer. This makes it trivial for your code to extract the result. Because CoT is about careful reasoning, you typically want deterministic behavior, so set temperature to 0. When the task is especially hard or ambiguous, you can layer on self-consistency by sampling multiple CoTs at a higher temperature and letting them vote on the final answer. Prompt engineering is not a one-shot activity. It's an ongoing process of designing, testing, and refining how you talk to LLMs. You'll often combine multiple techniques, system and role prompts, few-shot examples, chain of thought, tool use via React, structured outputs, and schemas to get the behavior you want. Configuration settings like temperature and max tokens are part of that design, not just defaults. By documenting your attempts and treating prompts as first-class artifacts in your code base, you can build systems that are both powerful and maintainable as models evolve.